Assalamualaikum warahmatullahi wabarakatuh. We are from group SCL2B. In our presentation, we will present about the electronic, optical and magnetic properties of the lanthanoids. My name is Aina Nabila binti Azhar and my group member is Shazana Amira binti Mat Shahar, Nur Ashika binti Rizwan and Muhammad Arif Fikri bin Muhammad Sanusi Badillah. So in our part, we present about the electronic properties and the optical and magnetic properties, which is contain the electronic absorption spectra, luminescence, and the magnetic properties. In my part, I will present about the electronic properties. First of all, in atomic state, all lanthanoids have the configuration xenon 4Fn CS2. N is the electron in the F orbital. Except for cerium, gadolinium, and lutetium because their 5p orbital is thinly occupied. And then the 4f orbital have no radical node because 4f electrons are fully screened from the nuclear charge and the electron-electron repulsion is significant. Next, the 4f outermost electron is well shielded by 6s and 5d electron. Consequently, it does not participate in the chemical bonding. Moreover, it cannot participate in the chemical bonding and the crystal field stabilization of the complexes, which is important for diploid elements. And then the outermost orbital is filled or empty, and it has a little effect on the chemical properties, but it does not affect the magnetic properties and their spectra. Next, the higher oxidation state generally occurs in chloride and oxide, but in lower oxidation state occurs in halide, which is bromide and iodides. Then the oxidation state of +2 and 4+ occurs when the lanthanoid 3+ ion lead to, firstly, a noble gas configuration. For example, cerium 4+ ion that have empty F orbital and then a half-filled F shell. For example, europium 2+ ion and the terbium 3+ ion that contain 7 electrons in the F shell. And lastly, completely filled F level. For example, ytterbium 2+ ion that have 14 electrons in the F shell. And then the +2 and the +4 state exist for elements that are closer to this state. And lastly, hence +3 state is the most stable, which is +4, and the +2 state have aqueous chemistry. For example, 1/4 cerium 4+ ion, then samarium 2+ ion, and lastly, ytterbium 2+ ion. That's all from my part. Thank you.
So I will compare the electronic spectra between the lanthanoid series and the d orbital series. So as you can see at the spectrum for the lanthanoid series, the peak is much narrow and high rather than the spectrum for the D block series, because the region is the ion of the most lanthanide ion absorb light in the UV and visible region. The transition involves only the redistribution of electrons within the 4f orbital are optically forbidden by the quantum mechanical station rule. Consequently, the compound of the lanthanide ion are generally red in color. Unlike the transition metal complex, the crystal or ligand field effect for the lanthanide 4f orbital are virtually insignificant due to the extensive shielding of the 4F electron by the 5s and 5p orbital. Thus, the FF absorption band are very sharp and the optical spectrum are virtually independent of environment. So I will pass to the next presenter.
Assalamualaikum and hi, my name is Nur Ashika binti Rizwan, matric number 202983. Okay, today I would like to talk about luminescence. So the important key here is lanthanoid, will show useful emission spectra application in phosphors, lasers and imaging. Luminescence also have two type emission, which are fluorescent and phosphorescent, where fluorescent is transition from higher energy state to one lower energy state that have same multiplicity, which is delta S equal to 0. And then phosphorescent is also long-lived transition from high energy state to one lower energy state that have different multiplicity, which is delta S is not equal to 0. And then the natural emission is limited by the low probability of absorption, which means that the excited state are not easily populated. Alright, okay, next, okay. This is the diagram for the lanthanoid trivalent cation. Okay, so the red line will represent as major excited state luminous level. Okay, after this, I will show you which part represent as red lines. Okay, so for the upward arrows for the P3+, PR3+, and upward arrow for the ND3+ is represent as the principal absorption line. Okay, and while the downward of EU3+ and the downward of TB3+ will represent as the principal emission lines for those ions. All right. Okay, so EU3+ and TB3+ have the strongest and most useful emission, where EU3+ will give the red lines and TB3+ will give the green line. So as I mentioned earlier, red line represent the major excited state luminescence level. So actually the red line is stand for EU3+. Okay, so the red line stated this region. Okay, so it will have the strongest and most useful emission. Okay, so EU3+ and TB3+ have the strongest and useful emission because both of them have large number of excited state, which increase the probability of inter-system crossing into the excited states of different spin multiplicity from ground state and give rise to the phosphorescence. Okay, and next is strength of emission also stem from excited electron interaction only weakly with its environment and having the low relative lifetime, which is millisecond to nanosecond. Right, next. Okay, so this is the Jablonski diagram. Okay, so actually luminescence can be greatly enhanced by placing a light absorbing group, or we call it as antenna, on ligand in complex. Okay, actually antenna is excited by allow the absorption to here, and then the energy will transfer either directly to the excited state or indirectly to excited state via energy transfer. Means that via intersystem crossing, and then it will go to the excited state of lanthanoid. Okay, so next, okay, so in electroluminescence, actually lanthanoid compounds are excited electrochemically. It is using the electrodes to inject electron into the higher orbitals of suitable organic group on ligand, and it will remove electron from occupied orbital. And then electroluminescent device based on lanthanoid also have been proposed for use in organic light emitting diode in OLEDs. Means that electroluminescent device will actually use in OLEDs. Okay, So luminescent also have the properties in lanthanoid, and their compound is a flourishing area of high technology. Okay. And then luminescent also have some applications where range across medical imaging, and then it also electronic. It also have application in electronic displays, and it is in encrypted signatures known as taggants. Okay, next. Right. So what are lanthanoid based on phosphors and lasers? Okay, so this is the spectrum of fluorescent lamp due to the lanthanoid ion in phosphorus. Okay, so first of all, okay, we talk about phosphorus first. Okay, phosphorus is actually fluorescent material that normally convert high energy to low energy. Okay, so the emission spectrum of EU that occur in range 580 here, 580 in EU, which is will give the orange color, and then orange color, and then it also occur in the 700, yeah, around this, from 580 until 700 nanometer, where the 700 nanometer will give the red color. And then TB3 plus, for the TB3 plus, okay, so TB3 plus is it is actually produce emission between 480, starting from 480 nanometer, starting from here, until 580 nanometer. Okay, until 580, yes, until 580 nanometer. Okay, so both of the wavelength will give the green color. And then EU3 plus, dope into YVO4 coated in interest of fluorescent light tubes, and it will convert the UV radiation that generate from mercury discharge into the visible light. Okay, so next is about lasers. Okay, so neodymium dope into garnet structure of yttrium aluminum oxide, or we call it YAG, Y3Al5O2, to produce material that used in neodymium yttrium aluminum oxide lasers. Okay, so we talk about lasers. All right, and then ND3 plus actually strongly absorb wavelength between 730 until 760 nanometer, and also in range 790 until 820 nanometer. And the large number of ion exist in a excited state. Okay, they can stimulate to emit light simultaneously, and also the very intense radiation will produce. Okay, next, the laser light at 532 nanometer or higher harmonics at 355 nanometer and 266 nanometer can be generated by frequency double of high intensity pulses. And then neodymium yttrium aluminum oxide also have the application include removal cataracts and unwanted hair, range finders, and lastly, it also involved in making plastic and glass. Okay, so I think that's all from me, and I will pass to the next presenter.
Okay, for the last part of this presentation is the magnetic optics. The core light of the ampere 4F electrons in lanthanoid compounds leads to exhibit magnetic moments in close agreement values predicted for the free ions based on the Russell-Saunders coupling. The spin of ampere electrons in the 4F orbital couple strongly with the orbital angular momentum but little interaction with the ligand environment, and as a result, the magnetic moment for a given 4Fn configuration is close to the value calculated for the free ion. Magnetic moment mu is expressed in terms of the total angular momentum quantum number J, as in the next slide. Mu is equal to Gj in the bracket J times in the bracket J plus 1
close bracket, power of half mu b. Gj is equal to 1 plus S times with in bracket S plus 1 close bracket minus L in bracket L plus 1 close bracket plus J times with J plus 1 close bracket over 2J in bracket J plus 1 close bracket. Mu B is the bond magneton while Gj is the Landis G factor. J is total electronic angular momentum, L is orbital angular momentum, and S is spin angular momentum. Long-range magnetic effects, ferromagnetism, and antiferromagnetism are also for many lanthanoids compound in solid state. In general, the coupling between metal atoms is much weaker than in the d-orbital compounds due to the contracted nature of the 4f orbitals that within the electrons. As a result, the magnetic ordering temperatures for lanthanoid compounds are much lower. I think that's all from our group. Thank you.